Hey, let's get started. Lots to cover today. The main topic today is recommender systems. You've probably interacted with these constantly in your online lives, movies, buying things, shopping, all that kind of stuff. So that's what we want to talk about today. And we'll frame the problem for now as let's find similar items. So you're on Amazon, you're browsing some item. What are some similar items that can be recommended? And our X matrix is going to have each example is going to be a user, and each column is going to be a product. And we're going to have an entry in there if that person interacted with that product in some way. It could be, did they buy the product? Did they rate the product? What score did they give the product? Did they write a review? Anything like that. We're going to record our interactions in X. And it could be binary or not, depending on what you're doing exactly. So a row of this gives me all the items bought by a particular user. A column gives me all the users that have bought a particular item. So here's the Amazon product recommendation method. A particular item is a particular column. So you're browsing, you're looking at some item, that's a particular column. Now we need to find similar columns to that column. So let's just use a KNN type thing. Except we're used to doing KNN across rows. Like find me rows similar to this particular one, but now we're doing KNN across columns. Other than that, the idea is basically the same. So we have some, I'm calling it X query, but the particular item that you're looking at right now that you want to query, and then for all other items, which ones are closest for some definition of closest. And there's a bunch of different ways that we can define close. And Euclidean distance is maybe the most obvious one or the most standard one that we've been using already in the course as our default for KNN classifiers. But I also wanted to draw your attention to cosine similarity, which is a popular metric for this kind of thing. So cosine similarity has its name because it's the cosine of the angle between two vectors. So the dot product, one way of defining the dot product is the norm of this times the norm of that times the cosine of the angle between them. So we can write the cosine of the angle like this. Dot product between two vectors divided by their norms. So what we want to do, if we're using this as this is a similarity measure rather than a dissimilarity measure, so we can maximize it instead of minimize it to find neighbors. Doesn't really matter. We can find the rows or items that are the closest to our particular item based on this, which essentially means find me the item with the smallest angle in vector space from the one I'm looking at. And the vector space now is the space of users. So this is the part that takes some getting used to, right? Each of these items is a column of the big X. Its length is n, the number of users. So your space that the items live in is kind of user space, where in the binary case, you're basically pointing in certain directions where those users bought the thing and not in other directions. So the cosine similarity is different from regular Euclidean distance, but it's the same as normalized Euclidean distance. So if I were to first take all the columns, divide them by their norms, and then use Euclidean distance, it's not identical in numbers to cosine similarity, but it produces the same ranking. So you'll get the same nearest neighbors. For me personally, the angle thing is a little more intuitive than thinking about normalized Euclidean distance, but you can think about it however you want. So one nice thing about this is that I'm planning on having you play around with some Amazon data in assignment 6, But what you'll see, and I'm sure this doesn't surprise you, is that X is a very sparse matrix. I mean, what fraction of all items have you bought, right? Probably, hopefully, not that many, right? So this X matrix maybe only has 100 non-zeros per row, and there's maybe 1 million items, so that's like 1 in 10,000 sparsity or something like that. So these matrices are very sparse, and as we saw earlier in the course, if you store a sparse matrix densely, you're just storing a whole bunch of zeros, then it might not fit in memory, but you might as well just store the non-zero entries, and that's really nice. If you do the normalized Euclidean distance route, then all the zeros, is that true? Now I'm second guessing myself. I guess if you're just dividing the entries by the norm of the vector, then 0 should stay 0. But if you're also centering, then you're going to get the zeros to be not 0 anymore. So it depends exactly what kind of normalization you're doing, if it's only scaling or if it's centering and scaling. Okay, so to build your intuition about what does a dot product mean between two of these vectors, if it's binary, so the person bought the thing or not, the dot product between two vectors is just a bunch of multiplications of 1s and 0s. You're only going to get a 1 if both entries are 1. So it's basically saying how many users are there that bought both of these products, and that's how you can interpret what the dot product means. Questions about this stuff? Questions or comments? Amit? Yeah. Amit, okay.
I'm guessing if the norm is 0, you just don't divide by the norm.
Right, yes, okay. So there's a special case to deal with if the norm is 0. Well, that's an interesting point. You probably wouldn't recommend that product if no one's ever bought it, or at least one question to ask yourself when designing a recommender system is, would I ever want to recommend a product that no one's ever bought? If so, does my approach do that? Or if the person's looking at a product that's never been bought, how do I deal with that? And we'll actually get back to that a bit later when we talk about movie recommendations. Okay, so an interesting effect of using cosine similarity as opposed to Euclidean distance is that it tends to return more popular items. And there's a sort of geometric intuition here that we're in this very high dimensional space equal to the number of users. X is probably very sparse. And basically, it's going to be hard to get a vector with a very small angle with you because, well, we can't really think that well in very high dimensions, but there's just so many directions these vectors could be pointing in that it's kind of unlikely that two of them will be pointing very, very close to each other. So here's a picture of what might be happening here. So if we're just looking at Euclidean distance, this bottom arrow is the query product, and this is in some fictional user vector space. If a lot of the angles are quite large, then the closest product might actually be a very unpopular one, because even the 0 vector isn't that far away from this query. You could get something much farther by being big and going off in the other direction. Whereas the second one that I'm calling xi here has a smaller angle, and so cosine similarity would prefer the more popular item. Euclidean distance would prefer the less popular item. So on the assignment, you'll play around with some data and see what happens empirically. And the thing about recommender systems, I mean, this is true for all of machine learning, but I found especially with recommender systems, there's so many different business reasons why you might want things to go one way or the other that it's hard to say, this is how I'm going to do it, right? You just sort of have to think through, okay, I'm going to do things this way. What's that going to result in? What kind of recommendations am I going to get? Am I happy with those recommendations or not? Okay, so when we talked about K and N a long time ago, it seemed like it was pretty expensive to make predictions because you need to search through all N training examples, compute those distances, which takes O of D time. And that's pretty slow because, well, I just talked about some possible numbers like 1 million users and 1 million items. So that's 10 to the 12 operations-ish. Things are getting pretty slow. So if the matrix is very sparse, there's some ways of speeding this up, but still things are very slow. And this is not just a recommender system problem, right? We've talked about k-means clustering. We had to compute distances. db scan, we had to compute distances. KNN, we had to compute distances. Whatever else is on here, we had to compute distances. So I'm not going to go into it now because of time, but there's a very large number of bonus slides if you're interested in what are the clever excuse me, what are the clever ways of speeding up finding nearest neighbors. And there's all kinds of interesting data structures that can store your data set so that you can make queries more quickly. Okay, so there's not even a single problem defined as what I would say the recommendation problem. For example, sometimes you want to recommend an item given an item. So I'm on Amazon, I'm looking at whatever, machine learning, textbook, and then given that I'm looking at that, you may want to recommend, even if I'm not signed in, so Amazon doesn't know anything about me, there's still going to be similar items at the bottom being recommended. Then you may want to recommend items given a particular user. So now given a row, I want to recommend a column. Instead of given a column, I want to recommend a column. And that's, for example, what Netflix has to do. So when you go into Netflix, I don't remember the latest numbers, but the vast majority of videos watched on Netflix come from recommendations, not people searching for stuff. And they found at Netflix that a very good predictor of whether people continue subscribing and paying the money is how much content do they consume through Netflix. So in a sense, their business is recommending stuff. I mean, obviously that's a huge oversimplification, but that is a core piece of their business. And if they can do that well, that's very useful to them. So that's given a user, you show up at a home page, you're not necessarily recommending a movie given another movie, but you're just recommending it for me. And then there's all kinds of variants on this, right? Maybe when you finish watching something on Netflix, it recommends the next thing. Or maybe with Amazon, if you're signed in, then it's given the item you're looking at and what it knows about you as a user. What can it recommend that's maybe more personalized than if you're not signed in and just looking at an item, et cetera, et cetera. So there's a whole bunch of cases of what I would call recommenders. And a very common way of phrasing the recommender system problem is that this X matrix contains ratings. So before we said it's did the person buy it or not buy it, and maybe it's binary, but it can also contain ratings. So on Netflix or Amazon or all these sites, you often give something 1 star, 2 stars, however many stars, and they have this big matrix of ratings. And one way of phrasing the problem is this is a giant matrix with a lot of missing entries, because I've only rated 100 movies. But if I could predict how I would rate all of the other movies, then I could find one that I would have rated highly and recommend that to me. So it becomes a problem of completing the matrix, in a sense, where you have some of the entries and you want to figure out what the rest are. Any questions about this? Okay, so how many of you have heard of the Netflix price? Just curious. Maybe 20%. Okay. So the Netflix prize was around 10 years ago, and it was one of these early machine learning competition type things where they gave you some training data, they had a test set, and people could compete. And there's a whole bunch of things like that now. You've maybe heard of Kaggle.com and all these other sites where you can, there's leaderboards and all these kinds of things. We may implement something like that for this course in future years. It's something we're thinking about. So here's an assignment, and let everyone just go at it and see who can get good test error. So there was a $1 million prize, which gave it a lot of media attention in order to reduce the squared error. So squared error, let me say what that means. It means Netflix had a whole bunch of ratings. They withheld some of them, so they made X even sparser than it really was by withholding some of the ratings. Then they had people predict all the ratings, and then they computed squared error between the predicted ratings and the ones that they were withholding. So their system, their baseline was beat almost immediately, but that's not that surprising. I guess you can just do random stuff and get it better by 0.0001. But the question was, could you do a lot better? And machine learning methods tended to dominate this competition. And some of the things we're going to talk about today and in the course in general came into play in this competition. I don't know how many of you have heard of Zillow.com, but they do housing stuff, and they're running a similar competition right now where people are predicting house prices. I think it's in progress. Okay, so there are many obstacles here. So it's pretty hard to predict whether someone will like a movie. So Napoleon Dynamite is, I guess, kind of a strange movie. People found it was very hard to predict whether someone would like it. I think I remember hearing that checking what day of the week the rating was made on ended up being very important to incorporate in the model, because people gave higher or lower ratings on certain days of the week, and you had to account for that or something like that. So this was a pretty hard problem, and it was hard to figure out what actually mattered in trying to predict these things. So the prize was eventually awarded a few years later, and it was a giant ensemble of a whole bunch of things. So in a way, you could team up with 5 people, everyone could work on it, and then once a week you could just ensemble all your stuff, and hopefully it would be better. So I guess I was saying earlier in the course that ensembling tends to be a good idea if you're trying to do this, right, which is get the best possible test error. But as I'll talk about in a few minutes, this is also kind of a mess to deal with if you're Netflix and someone says, oh, here you go, right? This is good luck integrating this into your production recommender system or whatever and maintaining it for the next 5 years. It gets a little more complicated. So a common theme in how this was achieved was using something called collaborative filtering, and that's what I'm going to talk about for the next few minutes today. So the funny part about this is that well, let's just go into it, and then we'll talk about why it's funny. Okay, here's our matrix. We're going to call it Y instead of X now. It doesn't really matter. We're kind of blurring the line between supervised and unsupervised learning here. I mean, you tell me, is this thing unsupervised? Well, I'm used to unsupervised learning, meaning someone gives me a matrix instead of a matrix and a vector of Y values. So I guess this kind of looks like unsupervised learning. But then I said mean squared error and all these kinds of things, validation, predicting, and then it kind of sounds like supervised learning, right? So it's somewhere in the middle, I guess. I'll call this unsupervised, but it's blurring the line a little bit. So this is what the data looks like, except much sparser than this. And we want to predict these missing entries. So I guess the first question is, how is there even hope? Like, I don't know, what are the missing entries supposed to be? Does anyone have any ideas of how one might approach this? Tom?
You can look at like the second and third rows and see that, for example, they match in all the ones that they have in ones 4, and then you can kind of do like perhaps a copy across. So where you're missing a 2, where you're missing the first element of row 3, you put a 2 because the other guy matches in all the other categories they match on.
Exactly. So what Tom said is you can look at the second and third rows and see, oh, those two users are pretty similar. For any time where they both rated something, they agreed exactly. So maybe I can use user 2 to fill in entries for user 3 and vice versa. So maybe I want to stick a 2 there for user 3 and stick a 5 over there for user 2. So what we're going to do kind of does that, but not so explicitly, because it becomes a big mess if you want to actually search through pairs of users and similarities and all these kinds of things. So that's the spirit of why it's not hopeless, but we won't take that approach directly. Okay, so let's say we have some randomly chosen user and some randomly chosen movie, and we want to figure out what to predict. And Tom was right on, so user 2 and user 3 are pretty similar in this case, and maybe that can help us. And likewise, column, whatever that is, 5 and column 6 are pretty similar. So most people agreed that on these two movies, so maybe they're similar movies, and we can try to use that information. Mohammed?
Why don't we use interpolation? Like
Why don't we use interpolation?
across the columns? If it's a big matrix, like
Wait and see what we're going to do, because it sort of does. We're going to use all the data at once in a way that I'm about to describe. So I think this is maybe the most important slide in the lecture, or at least the one where there's the most going on conceptually. So the punchline is this. We're just going to take that matrix Y and run PCA on it. And then we're going to get our reconstruction of that matrix, and the reconstruction will fill in the missing entries because we'll take Z times W and it'll just produce a whole matrix for us. And somehow that's going to do the job. So the big conceptual task of today's lecture is to understand, what does this have to do with PCA? It seems like it's coming out of left field, and we need to get our minds around that. So here's the idea. PCA says, we're calling it Y now instead of X. Hopefully that's okay. But PCA says Y gets factorized into Z times W, which means each entry of Y, Yij, is the dot product of some row of Z with column of W, which is exactly what's written here that notation looks fine. So here's what we're saying. We're saying that we're creating these k new dimensions. With PCA, we pick k, and you could say, well, each user starts as a d-dimensional vector, which is how they rate every movie, and we're mapping each user down to a k-dimensional vector, which is this new space that who knows what it means. And we can try to interpret the new space as a kind of mapping from users to movies. So for example, the first new direction, the first out of k new features that we've invented, maybe that represents something like the person likes watching romantic comedies. And then maybe on the movie side, that corresponds to this movie is kind of romantic comedy-ish. It has elements of a romantic comedy. So we're basically saying for each movie, you get to come up with some new vector of length k that lives inside of W. And for each user, you get to come up with some new vector of length k that we have one for each user. And we're just going to multiply those things together to get a rating. So if this user really likes romantic comedies, they have a really positive entry there, and the movie is a very romantic comedy, like there's a positive entry. When you take the dot product and you multiply, you'll get a big number. Or if the user really hates romantic comedies, you have a negative number, and the movie is completely not like that, has a negative number, you'll multiply and get a big number. But the thing is, we're not telling PCA about this concept of romantic comedies. We're just saying, you get to decide everything. The only thing I'm giving you is this matrix. You invent what this k-dimensional space is going to be, and do it such that when I take these dot products, I kind of get the right answer. The reason why this is very confusing, at least to me, is that with PCA, when we talked about it last week, we had a pretty strong asymmetry between our interpretation of Z and our interpretation of W. The math is all the same, but the way I think about it is pretty different. Because we said Z is the new feature vector for each example, and W are the basis vectors. But now, users, movies, whatever, right? They're all kind of things that we care about. It's not really like one is the features and one is the examples. It's that the movies are the features for the users, and the users are the features for the movies. So there's this kind of new symmetry. And so W and Z kind of respect that. And so I would think about each row of Z as the new feature vector for each user. And I would now think about W in a very different way than we used to think about it. Instead of thinking about W as the rows of W are basis vectors, I think you should now think about W as the columns of W are the new feature vectors per movie. Because W is k by D, and we have D movies. So each column of W is this feature vector for that movie, and then we're just dot producting these things together. It's all just minimizing some objective function in the end of the day, but we can think about it as learn these features automatically and set all these numbers so that it all kind of makes sense. And the thing is, if there's 1 million movies, then a vector for each user is length 1 million, but that's like a huge vector, right? So the hypothesis is I don't need 1 million numbers to represent a user. I can represent a person more concisely than their rating for every single movie ever. Maybe there's just 100 things about a person, 100 features, and I'm going to try to learn those automatically. Okay, that was a lot of talking. Anything from you guys?
What's Z again, like in your explanation?
Z is, we still have a row of Z per user, and it's the new feature vector for each user. So for each row of Z corresponds to a user, it's length k vector that is the k features for that user. Anna?
So I and j always have to be equal, like the numbers?
I and j don't have to be equal, but k has to be the same k on both sides, meaning Z has to be n by k and W has to be k by d. But that's kind of just a matrix multiplication necessity.
But I mean, the features that the users have must be the same number of features that a movie has.
Yeah, which is k. The number of features that a user has equals the number of features that a movie has equals k. So it's just when I use words in English to say what those features might mean, I just have to use slightly different words. It's the same feature, it's just the number in position 1 if it's feature 1. But the number in position 1 in Z, I'm just trying to turn into words, and maybe it's that user likes romantic comedies, and the number in position 1 in W, meaning row 1 in W, I would just describe it a little differently, but they're actually the same feature. It's just kind of the romantic comedy feature. And again, PCA may not learn about romantic comedies, and it's certainly not going to give you the interpretation of what these features mean. It's just going to give you two matrices, and that's all you get. Jeannie?
How do you represent the missing entries from the original Y?
Yeah, great question. How do you represent the missing entries from the original? So, I think I have this somewhere, but by default, you'll just leave them as 0. But that's kind of the first thing you could do. The problem if you leave them as 0 is that they might dominate your loss function, because your loss function is just the sum over all entries. And if 99.999% of your entries are missing, your loss function is dominated by trying to reconstruct some number that isn't a real piece of data. So we will get to that soon about how to get around that. But yeah, it's a good question. Oh, it's right here. OK, good. So next slide. How do we deal with this? So if we just took PCA out of the box, like the PCA code that you were given on the assignment, or scikit-learn PCA or whatever, out of the box PCA, it's expecting a dense matrix. So it's just going to try as hard to reconstruct those zeros or missing things as it is to reconstruct everything else, which isn't that great. So we can define our loss like this. That loss is the PCA loss. It's the same thing. But the sum is only over the place where we actually have ratings. That's kind of what we want, right? We want to reconstruct the things that we actually have. But we can no longer use the SVD to do this for us. Because the SVD, give me a matrix, I'm going to factorize it in this beautiful way with all the properties that we talked about. But if we want to do this loss, which is only on the entries that we actually have ratings, then we have to do some sort of gradient descent type thing. And like we talked about last time, we should add regularization so that W and Z are not allowed to just go arbitrarily crazy, which the SVD prevented due to the vectors being orthonormal. But here we take matters into our own hands. Yeah. So this weird extra regularization thing is just an aside. It's not that critical, but sometimes instead of completely throwing away the missing entries, people will keep them around, but downweight them. Like I think in one of your early assignments, you had a weighted linear regression where you gave outliers a lower weight. So you can do the same sort of thing. Stick the missing entries to be, say, the average rating, and then weight them really low so they don't count that much. But it's a little bit of a penalty for predicting something different from the average, which is basically a regularization, saying don't do anything too crazy. That can help in addition to the regular types of regularization. OK, this is an important slide as well. Any other questions about this? It's important to understand what the problem is. Basically completing a matrix, filling in missing entries. The business motivation of this problem was making recommendations. The surprising fact was that you basically just do PCA, even though we never talked about completing a matrix really. I mean, we talked about reconstructing a matrix with PCA, but not completing it. And then there's this key idea that I don't want to reconstruct all the entries. I just want to, my loss should only include the ones that I actually have. OK, so we can spice this thing up a little bit. We can add an intercept or bias term that we also train in addition to W and Z that allows for a global scaling, or we can even add user-specific biases. So we can learn an intercept for every user. Maybe this user just likes movies, and this other movie is just a horrible movie, and we can learn those things as well. So that's not really a big conceptual change. It's just the usual business of adding in intercepts. But we can actually decide to add a lot of intercepts, not just a global one, but one for each user and one for each movie. And maybe we want to regularize those as well if we feel like it's overfitting to have so much flexibility in our model. Okay, so this is what I wanted to say earlier. Congratulations, you won the Netflix prize with an ensemble of 100+ models, but the objective function of Netflix and the objective function of the prize were kind of misaligned, because Netflix wanted to improve their product, and their proxy for that was test error, but they didn't regularize, or however you want to say it, penalize things that they didn't like, right? That's kind of what regularization is. So they could be like, your score is test error minus lambda times number of lines of code, or whatever, right? That's basically regularization, right? But they didn't do anything like that. And so it's just good to point out this, to keep in your mind this alignment of always focusing on your score, but then what are the actual objectives for what you're doing? I mean, yeah, just maintaining, getting better recommendations makes you money. Needing to hire an extra 10 devs to deal with this code on a daily basis costs you a lot of money too, right? So it's complicated. Right, so speaking of the objective function, even just the messiness of the code aside, maybe your test is not just all about test error. So maybe you want to impose some sort of penalty on the diversity of the thing. Maybe the person really likes Star Wars and you just recommend Star Wars 1, Star Wars 2, Star Wars 3, Star Wars 4. Maybe that's not as useful as having more diverse recommendations for that person. Another thing is this issue of persistence. So if I don't click on something for a month, then even if the algorithm still thinks it's the best, maybe it's not the best anymore. So that's a kind of training data in a sense, right? That I didn't click on it. This issue of trust and interpretability. So, Rob, you might be interested, right? So this issue of, well, why did you actually make that recommendation may make someone more interested to click on it or feel more comfortable or trust the recommendation or not be freaked out, right? So you've maybe heard of the story, famous story about Target or Walmart. I think it was Target mailing some brochure about diapers or something, and there was a young girl whose father got really upset and called Target and said, "What are you doing? My daughter's not pregnant, blah, blah, blah." But then it turned out she was pregnant, and he didn't know, and it was this big mess, right? So they knew just by her activity, online activity, or I don't remember how long ago this was, maybe not just online, but that's weird, right? So there are some issues here when you make recommendations that even if diapers are like the lowest error, predicted error, or whatever, maybe you don't want to recommend them. It's complicated. This issue of social recommendations, so you can incorporate extra information, like this matrix isn't everything you have. Maybe you want to look at the people's friends. And maybe you want to look at new things. So a major weakness of this unsupervised approach that I've been talking about is if I had a new movie, and this goes back to Amit's question from earlier, if I had a new movie, that's just a column of zeros because no one has rated that movie yet, it's brand new. So how am I supposed to recommend it? And if I had a new user, if I joined Netflix, I don't know anything about me because I haven't rated anything yet. So this collaborative filtering approach is a little bit weak on that side of new stuff. And you could do something like you could just look at those bias terms and say, well, which movie has the highest beta? Like that's the most popular movie, period, and I'll just recommend those to this person. But it is a weakness of collaborative filtering that it's hard to get started with new items or users. we talked about this. Whoops, this unsupervised approach. We just have this big Y or X, whatever you want to call it. We just have this big matrix, sparse matrix with ratings, and we want to predict stuff. But there's a completely other approach to recommenders, which is a supervised approach, which says, what if I have extra information about the user, such as their demographic information, amount of time on the site, friends, all these other things. And what if I have extra information about the movies, like its genre, year, like blurb about the plot that I can get some text features about, et cetera, right? So I actually have features, and I can just treat this as a supervised learning problem and say, well, given this person and this movie and their person features and their movie features, what's their rating going to be? So this is nice because when a new person or a new movie shows up, you're going to have those features and you can just immediately make predictions. Yeah. Okay, that's fine. So this is just showing that the math for those two things look kind of similar, except that in the supervised case, you actually have the feature. So now I understand this motivation for changing X to Y. So now we actually have the features, which we're calling X here, whereas in the unsupervised case, we're kind of learning the features, which is this unsupervised stuff I was talking about. Okay, so by the way, this is saying it's a linear model, right? You don't have to use a linear model. You can use whatever you want to do this supervised learning. Okay, so SVD feature refers to the idea of combining these two things. SVD, like the PCA unsupervised part, and feature, like the supervised part, I'm assuming. So you can just combine these into one giant model and one giant loss function and just optimize this huge mess of stuff, and you'll actually get pretty good results. So you're simultaneously learning the latent features and leveraging the features you actually have. Okay, that's fine, that's fine, that's fine. Right, so this is saying all those first four terms are just standard linear regression stuff, and then we have this extra PCA type thing. So this is one of the cases where I'm already adding so many things together that I'm thinking, well, this probably doesn't work, it's too messy, but it actually does work, right? So it's nice when things this complicated actually get the job done, and it does happen. Okay, I think I talked about this as well. So I mentioned this briefly, that you can try to use friend information for these predictions. Any questions or comments about this? Amit?
The betas that you learn, would they be put into your matrices, and then like the beta itself is actually what you this out?
The betas that you learn, the intercepts, so those are just separate. They're not incorporated into the matrices. Yeah. So I haven't thought about it too much, but it seems to me like this column of ones thing is not going to work out here. And so we just treat those separately. And as long as we can compute the gradient of the loss with respect to all those things, theoretically, we should be able to just optimize the whole thing. Okay. Bit of an awkward amount of time left, but we'll see how it goes. So something that I don't really want to talk about, but I feel like I'm supposed to talk about, is association rules. So I've just compressed it from an entire lecture into 3 slides so that it's making an appearance. And well, it's not necessarily because these aren't useful, but I don't have much personal experience with them, for one thing. So association rules come from the sort of data mining view of these things. And again, this issue of people are shopping, they buy stuff, but it comes from the kind of supermarket idea that you buy a bunch of things together. So let's try to learn what things tend to be bought together to try to make recommendations and all that kind of stuff. So if you have some set of items, in this case sunglasses and sandals, and some target item like sunscreen, then association rules are rules of the form, if I bought these things, then I'm probably going to also buy this other thing. Or that tends to happen. And we, excuse me, we have to be a bit careful about causality, but we're just looking for associations here. So when we talked about clustering earlier in the course, we talked about grouping together the rows, which rows are similar, and you can think of association rules as grouping together the columns. So if these things are 1, meaning people buy them, then this other thing is probably going to be a 1. It's also going to be bought. So in general today, we kind of have to be comfortable with transposing X because we're doing stuff with rows and columns in ways that we don't usually do. So the way association rules work is that there are 2 quantities called support and confidence. And essentially, the type of rules you're looking for are the original set S tends to occur frequently. So I'm looking for rules that this actually happens, and when this happens, this other thing also happens pretty often. So support refers to how often S happens, and you can think of it as a probability, and you can think of confidence as a conditional probability given people bought the stuff in set S. What's the probability of buying the target item T? And all the slides on this have been moved into the bonus slides, so you can read about this if you're interested, but I wanted you to at least be aware that such a thing exists. If you hear about the a priori algorithm, it's a clever algorithm for finding these sets of high support. So you run into this issue that the number of subsets is exponentially big, and you need to do some cleverness to search through all of them to find good candidate sets, and then you can check to see which ones have high confidence. So there's this issue here of multiple comparisons where you're searching through such a huge number of possible rules. You might get some rules that look great but are just great by luck. So talking about causality and all that, inference is something we don't do really much in this course, but should be covered in the stat curriculum. I don't know exactly which courses. And there's also all kinds of good stories here too. So there's I already told you the target story, but there's this beer and diaper story that people found those 2 things tend to be bought together on Friday afternoons or something like that. And I think this lecture is interesting because you really have to keep the loop closed between the machine learning side and the business side. Like, do I want to advertise those 2 things together? I don't know. Or I could think of things that I might not want to advertise together, right? But I can't think of all of them in advance and somehow eliminate them. So I kind of have to keep my eyes open as I'm programming stuff. I was even more absurdly optimistic than usual on time, so I have to skip ahead to the next part. But to conclude, what we did today, talked about what is a recommender system. We talked about using nearest neighbors to find similar items with Euclidean distance and cosine similarity. We talked about collaborative filtering, which was this weird thing of using PCA to fill in the missing entries. And maybe we don't want to do the full PCA, but we want to restrict the loss to only try to reconstruct the entries that we actually have, so we can't use SVD. So we use gradient descent or SGD or some other thing is fine. Then we very briefly talked about, didn't have time to say that at one point, which is one other way you can recommend things is you can do the PCA thing, then you have latent features, then you can do nearest neighbors in that latent space, and then Euclidean distance might be a lot more meaningful. So the W vector for one movie and the W vector for another movie, if those are similar, then you might want to link those two movies together. And then we briefly talked about association rules and didn't have time for the last stuff. So that's it for today, and I will see you on